In this section, we're going to talk about section 4.3, which is about finding the probability of compound events. And we're going to do that using the addition rule. Okay, so first we need to talk about what a compound event is. And a compound event is an event that combines two or more simple events. Of a procedure. So for example, maybe you'll want to know what's the probability if you're rolling a six-sided dice of getting a 5 or a 6, that kind of thing. Okay, so another term we need to define is called mutually exclusive, and sometimes this is also called disjoint. So given a random procedure, two or more events of the procedure are called disjoint. This is the same as mutually exclusive if they cannot occur at the same time. So if they cannot occur at the same time, they're disjoint. If they can happen at the same time, then they would not be disjoint. So some examples of this, if we're talking about flipping a coin, you can't get a head and a tail at the same time, so these would be disjoint. If you're drawing a card from a deck of cards, you can't get a king and a 2 in the same card. Okay, now something, for example, that would not be disjoint, if we're talking about drawing a card, you could get a red king. So a card being a king and a card being a red would not be disjoint. Okay, so disjoint means they cannot occur at the same time. Okay, so now we get our rule of how to find our first probability of compound events. So if events A and B are two outcomes of a random procedure, and A and B are disjoint, so this rule only works if they're disjoint, then the probability that A or B occurs, so we're saying the probability that A or B happens, is the probability of A plus the probability of B. Now, adding two probabilities means that it's larger than any of the two probabilities by themselves. And this should make sense. If we said, if we flip a coin, what's the probability of getting a head or a tail? Well, that would be 100%, where the probability of just getting a head would be 50%, and the probability of getting a tail would be 50%. So together, they would be 100%. Okay, so here's another example. It says we have 6 colored dice in a bag. It doesn't really matter that they're dice, but just think of 6 colored objects in a bag. 3 of those objects are red, 2 are green, and 1 is blue. We're going to pull out 1 dice. So we want to know, for that 1 dice, what's the probability that it's green or blue? Now, since none of our die are both green and blue, they're just solid colors, this is a disjoint event. If we pull out a dice or a die, it can't be both blue and green at the same time. So this is going to be the probability that it's green plus the probability that it's blue. So the probability that we pull out a green die is 2, because there's 2 green die out of the 6 die. Plus the probability of a blue die is 1, because there's 1 blue dice out of 6. Okay, so we add these together. We've already got our common denominator, which will happen most of the time. So we get 3 out of 6, which is the same thing as 1/2. So a similar problem says we roll a 6-sided dice 1 time. Okay, so just a normal die. We want to know what's the probability that we roll a 5 or a 6. Now, when we roll a dice, we can't get a 5 and a 6 at the same time. So these are disjoint. So this would be the probability of getting a 5 plus the probability of getting a 6. Now we know rolling a dice, each number has a 1 in 6 chance of coming up. So the probability of getting a 5 is 1 out of 6. And the probability of getting a 6 is 1 out of 6. So the probability of getting a 5 or a 6 is 2 out of 6, or 1/3. Okay, so what you should be noticing is that when we have the word or in our probability, we add. Okay, and that's why it's called the addition rule. Okay, for our next problem, it says choose one of 4 cards. And so this is kind of a notation to make it easy to write out. We've got the King of Clubs, the King of Diamonds, the Queen of Diamonds, and the Jack of Clubs. So the first thing is the kind of the face or the number, and the second thing is the suit. Now, this asks us to find the probability of a king or a diamond. Now, is king and diamond disjoint? No, it's not, because we can have the King of Diamonds. That can happen on one card. So we can't quite use our rule here. So let's just look at these 4 cards. Of these 4 cards, we're not talking about a whole deck. How many of them have a king or a diamond in them? Well, we've got the King of Clubs, the King of Diamonds. So those are the ones with the kings. And then we also have the Queen of Diamonds. So here we can see we have 3 out of 4. Now, if we just blindly tried to use our rule, even though these aren't disjoint, then we would take the kings, we would have had 2 out of 4. And the diamonds, we would have had 2 out of 4. And if we had added those together, we would have had 1 or 4 out of 4. But we see that not all of these cards are a king or a diamond. We've got this Jack of Clubs. So what was really happening, if we just tried to do our rule, is we were counting the one that was both twice. Okay, so that would have messed it up. So when they're disjoint, we can't use our rule the way it is. Okay, so if 2 outcomes can both occur at the same time, then we say they're not disjoint. Okay, or another way of saying that is not mutually exclusive. Okay, so here's our rule. If 2 outcomes are not disjoint, then the probability of A or B, we take the probability of A plus the probability of B, and then we've overcounted some. So then we subtract the probability that A and B both occur at the same time. Okay, so we have to subtract the ones that we've counted twice. So if we look back up and we use our rule for the problem about the king or diamonds card, well, how many kings did we have? We had 2 out of 4. And how many diamonds did we have? Well, we had 2 out of 4. And then we're going to subtract how many were kings and diamonds. And that was one of the cards, so minus 1 out of 4. So here we get the correct answer of 2 plus 2 is 4, minus 1, we get 3/4. Okay. Our next example is kind of fun. It's about a pet store. So this pet store has cats, rabbits, and gerbils. And we see they've got different numbers of each type of animal. So, for example, they've got 7 black cats and 4 yellow cats, 8 black rabbits, 3 white rabbits, 3 orange gerbils, and 5 white. Now, I don't recommend actually doing this, but, for our theoretical probability question, we're going to place all the animals in one area and randomly choose them. I don't suggest this for a couple reasons. 1, I'm a little worried about the gerbils and the cats being together. And 2, I don't think it's probably safe to just reach your hand in without looking randomly. But anyways. Okay. Now, we probably want to know a couple things. We need to know how many total animals there are. So let's get this. Let's get total cats. We've got 7 black plus 4 yellow. So we've got 11 total cats. Total rabbits. We've got 8 black and 3 white, so again 11. In total gerbils, we've got 3 plus 5, we've got 8. Okay, so total animals that we're putting in this pen together, 11 plus 11 plus 8, we have 30 total animals. Hopefully they all survive the problem. Okay, so first we want to know what's the probability of getting a cat if we randomly pick one. So we're going to take the total number of cats, so that would be 11, over the total number of animals, over 30. Okay, then we want the total the probability of getting a rabbit. So we would want the total rabbits, which is 11, over the total animals, which is 30. Next we want, what's the probability of getting any white animal? So we need to look and see what are white animals. We have 3 white rabbits and 5 white gerbils. So that gives us a total of 8 out of 30. Okay, now we could reduce this to 4 out of 15. Okay, now we want to know what's the probability of getting a cat or a rabbit. So since we have or here, we're going to use our addition rule. So the first thing we have to figure out is, are cat and rabbit disjoint? Now, since in one animal we can't have a cat and a rabbit, if we just pick one animal out, this is disjoint. So we're going to take the probability of getting a cat, which is 11 out of 30, plus the probability of getting a rabbit, which is also 11 out of 30. So we've already got our common denominators, and we get 22 out of 30, which we can reduce to 11 out of 15. Okay, and the next one says, what's the probability of getting a cat or a white animal? Now we need to ask, is this disjoint? Can we have a white cat? Now, out in the real world, I'm sure some of you have seen white cats, and you might think, oh, it's not disjoint. But in this particular pet store, we don't have any white cats. Our cats are only black or yellow. So for this instance, it is disjoint. So we want to take the number of cats, the probability of getting a cat, which is 11 out of 30, plus the probability of getting a white animal. And what I recommend is take the one before it's reduced. So 8 out of 30. That way you have your common denominator. So we get 19 out of 30. Okay. Next, we want to know what's the probability of getting a rabbit or a white animal. Okay, now in this case, we do have white rabbits in our pet store, so this is not disjoint. So we need to take the probability of getting a rabbit, which was 11 out of 30, plus the probability of getting a white animal, 8 out of 30, minus the probability of choosing a white rabbit. So since we have 3 white rabbits, that's going to be 3 out of 30. Okay, so that gives us a total of 16 over 30, or 8 over 15. Okay, and finally we want to know what's the probability of getting a cat or a black animal. So again, in this pet store we have black cats, so this isn't disjoint. So we need to know what's the probability of getting a cat, which we know is 11 over 30, plus the probability of getting a black animal. So we need to figure out how many total black animals we have. We have 7 black cats and 8 black rabbits. So that gives us a total of 15 out of 30. Minus, now we need to subtract the ones that overlap. So since we have cat and black, so the black cats, we've got 7 of them. So minus 7 out of 30. Okay, so we need to add this up. So we get a total of 19 over 30. Okay, our next problem is about a party. There are 25 men at a party. 10 of the men are bald and 17 of the men wear glasses. So you're going to randomly choose one of the 25 men. And the question is, what's the probability that the man is bald or wears glasses? Okay. So now the first question we need to ask ourselves is this a disjoint situation? Can one guy be bald and wear glasses? And the answer is yes. Okay. So we want to take the probability of getting a bald guy plus the probability of getting a guy who wears glasses. Okay, and then we need to subtract the probability that a guy is bald and wears glasses. So now you might see we're missing some information. We know that 10 out of 25 of them are bald, and 17 out of 25 of them wear glasses, but we don't know how many are bald and wears glasses. So that's our problem. And you can see that we know at least one of them or a couple of them do, because if we added these, we'd get 27 out of 25, which is more than one, can't happen. So to actually do this problem, we're missing some information. We can't do it. So you do have to be careful about when things are disjoint. Okay, one more problem for our addition rule. So the problem says, for a small town of 100 kids, the following table shows how many of the kids have or do not have toy cars and toy trucks. Okay, so in the columns, it tells whether a kid has a toy car or not. So we've got some who do have toy cars and some who do not have toy cars. And then we can ask, do they have a toy truck? And the answer is either yes or no. So this first number, the 35, means there are 35 kids who have a toy car and they have a toy truck. Okay, the 30 here means they have a toy car, but they do not have a toy truck. Okay, and so on. So the question says, if you randomly selected just one child from this town, what's the probability that this child either has a toy car or does not have a toy truck? Okay, now these aren't disjoint because there are some people who have cars and don't have trucks. So we want probability of has car or does not have truck. So since these aren't disjoint, we're going to take the probability that they have a car plus the probability that they do not have a truck minus the probability that they have car and no truck. So out of the 100 kids, we can figure out how many of them have a car. So that's the first part. So we look at this first column. Those are the ones that have a car. So 35 plus 30, or 65 out of 100 of them have a toy car. Okay, now the ones that do not have a truck, that's the no for the trucks. Okay, so that's the 30 plus the 10, so we'd get 40 out of 100. Okay. Now we need to subtract the ones that have a car and do not have a truck. So that's the one here that we've overlapped, the 30 out of 100. So here we can see if we take 65 plus 40 minus 30, we get 75 out of 100. Okay. Which we can reduce to 3 out of 4.